Okay. Now, a simple logic gate takes into what? Inputs you get, and it generates one output. Two inputs and one what? One output, as we are going to see. So each input will either be on, or what we can call true, or it can be off, what we can refer to as false, meaning it carries voltage or it does not carry. So the output will always be either on or off. Yeah. So depending on the condition that particular gate is aimed to do what? To fulfill. So like I have told you, by combining tens, hundreds, thousands, and millions of logic gates, it makes it very, very possible for computers to perform very complex operations at a very high what? At a very high speed. So each particular type of logic gate has a predetermined set of what? Possible input and stock output combinations, as we are going to be seeing. And the best way to describe a logic system is by using what we call the truth table. Yeah, once we have the truth table, then it becomes very easy for us to determine the state of the logic system we are dealing with. So the truth table is a tabular layout which shows the relationship between the output from a logic circuit and all possible inputs to the circuit. So you realize that both outputs and inputs are expressed in terms of what? Zeros and ones. Yeah. So these are just a few definitions. Like now for a digit circuit, logic gate is a digit circuit with one or more inputs and an output, which depends logically on the input signal what? Combinations. And then when we talk about the gate specifically, we are referring to that PC circuit, which that comes with several inputs, but only one output that can be activated by a particular combination of inputs. Here we may have, a chip, as you can see, sample. Then the legs of the integrated circuits are used to feed the signals from the micro manual system inside the device to the output world. And we are going to be dealing with what you have to know is that there are 7 logic gates represented by specific symbols. We have what we call the AND gate, the OR, the XOR, the NOT, the NAND, NOR, and XNOR. So each gate performs a particular logic what? Function you get. So like I have said, these 7 logic gates, each one has a unique what? A unique symbol. I need to let me add something here, add something small so that we get to see these what? These symbols. Yeah, actually, I think we can proceed with this. Now, this is the AND gate. Now, the AND function is implemented electronically using the device known as the AND gate. So, and this is the symbol that represents the AND what? The AND gate in this sense. Gate. This is what I want you to note. Every time you see this, then it is a representation of the what? Of the AND gate. The gate. So, and the AND gate derives its name from the fact that we get an output of true when both the inputs are true, else the output is a negative one or a false. Please, I want you to note this. Like each logic gate has the condition that determines the state of the output by following what has been inputted. Therefore, for example, when we talk about uh, uh, the and gate, this very one, you realize that the rule for the and gate is that the output is one or is true when both inputs are true. We are going to very good, very good. It is here. Now let's look at this relationship between the semantic and the logic operator known as the what? The AND operator. If the car is fueled and the engine starts working, then the engine will do what? Will automatically start. I have told you that on this logic gate, just note the what? The condition, and the condition for the AND gate is here, whereby you can only and only get the output of one or true when both inputs are what? Are true. The moment one of the inputs is not true, then the output obviously becomes 0 or false. You get? So now look here. We have our truth table here for the AND operator. You get? Now, meaning that if we have input A and we have input B. These are the ones that it determines the what? The output. Now, remember our condition states that the output can only and only be true if both inputs are what? Are also true. But the moment one of the inputs is not true or is not one, then the output is obviously 0 or what we refer to as what? False. That is why you see when our input A is 0 and input B is 0, or they are both false, obviously the output has to be false. And if input A is false, but input B is true, that does not determine the true output, but it also remains false or 0. And the same appears here. But where, in cases where both inputs, I don't know what is wrong with this sound people. We always encourage that when you join a class, try to mute so that we don't get a lot of noise. Kafumbe Marvin, I'm muting you for the last time. The moment I get your noise again, you will automatically find yourself somewhere that you will even, let me pause it at that. I was still emphasizing on the AND gate. Our condition says that the output can only and only be one or true if both inputs are what? Are true. Else, the output returns what? 0 or false. That is why you are seeing this truth table representing a true or a 1 here, because both inputs, that is input B and input A, are all what? Are all 1 or true. So, and means that both conditions must be true in order for the condition to do what? To be true. If the car is fueled and the engine works, then the engine will do what? Start. So the AND means that both conditions, input A and input B, have to be what? Have to be true for the output also to be what? To be true. Yeah. So I think I need to, okay. We have the mount input and get, whereby the AND gates can be built.
Excuse me.
Yes, please.
Excuse me.
Yes,
Sir, I wanted to ask you on that and get on your output what you were displaying there, but I'm not still seeing.
let me display again. Here.
There, sir.
Mm.
Now, say I'm in paper and you bring such a table for me of A and B with output, and you ask, how do I come to know that it is and? I thought you would say A and B, then you start putting out the output.
You come again.
They are on the truth table that you are showing there.
Yes,
You are
please.
showing A, B, then output.
Yes.
What if for me I say, what if I say A and B for easy identification, because I can easily not get with your output. You might be putting out of either of O or no. What I'm not getting this.
Okay. Let me hope me I have got you well. And now this letter A represents input A, or I mean the first input. And this B represents the second input. And it is the inputs that determines the output. So, and our condition is that for the AND gate, both inputs, either, actually, even if we had not used the maybe A and B, and maybe we had input 1 and then input 2, then the output. So, in both inputs, input 1 and input 2 must be true for us to have a positive or a true output, which is represented by what? By 1. And in case any of the two inputs is false, automatically the output will also be false, which is represented by a 0. Remember, you are dealing with binary numbers. It is either 0 or a 1. And you realize that each gate has its own what? Logic or set of rules that determines how it acts based on multiple what? Inputs using the truth table. And now we are focusing, our focus on this one is on the what? On the AND gate. I don't know if my rebuttal has made some sense to your question.
Yes, sir, it is true.
Yeah, but where you have to put the emphasis is on the what? On the condition, because each gate has its own what? Logic or set of rules that determines how it acts based on multiple inputs. So, meaning that for the AND gate, both, I mean, in case we need to have the true output, then both the inputs must be what? Must be true. And you know that our true is represented by 1, and then the false is represented by a 0. So now in this case, if the output is true, then this can only be possible if input 1 and input 2 are both what? Are both true. That is like here, if we have 1 and 1, obviously this is going to be 1. But in this first scenario where you have 1 input and then another input is false, then obviously the output must return a what? A false or a zero. Okay, I want us also now to look at the all. But even when we were starting to learn computer organization and architecture, I told you that most of the terminologies are based on what they perform. For example, the way how someone can say, you know, a CPU is the brain of the computer, meaning that that component is the one that thinks for the what? For the rest of the components. It is what makes the computer to think. So now, in this case, and meaning that both A and B must, because, you know, that is why you used the example of a car. If the car has received the fuel and then the engine starts, I mean, it works, then obviously the engine can do what? Can now start. But if the engine has no fuel, fine, the engine is working well, but it has no fuel, then there is no way how the car or the engine is going to do what? To start. But for the engine to start, it has to be working well, but also with what? With fuel. So both conditions must be true for the output to also be what? True. So now when we go to the all, as you hear all, and let me look at if we have some, if I have some symbols here, I want, yes, look here. The all get derives its name from the fact that we get an output of true if any of the two or both of the inputs are what? True. Meaning that the car can start, and now I'm just using that very example, but it is not the reality. If the car's engine is okay, even if it does not receive fuel, but it can do what? The engine can start. That is in a case maybe our engine now is electronic in nature, that yeah, you don't need to put fuel so long as there is some battery. I mean, this can do what? Can start. So now they all get where echo is coming from. Kaira Edward, you're producing a lot of echo. Kindly spare our ears. Thank you. I was still telling you that the all get derives its name from the fact that we get an output of true if either or both of the inputs are true, whereby if inputs are, or like if both inputs are false, then the output is automatically also gonna be what? False. And that gate is represented by this symbol. This is all you get. So for us, look here. If I have cash or credit card, then I can pay my what? Pay my or I can buy your car. That is in case I have money on mobile on my mobile account on my Momo Pay, and maybe I have cash, I can go to any fuel station and buy fuel. You get, meaning that any of the two options can work or work such that the output is true if either of the two inputs is what? If I decide to go to the supermarket with the cash, I can get what I want, meaning the output is true. If I go with the cash, I can get At the same time, if I go with the mobile money, I just use their merchant code to pay, I can still get the products. So that is all you get. So that is why you see that we have our input A and input B that are going to be used to determine the what? The output. If I go to the supermarket without cash and I also don't have mobile money, then there is no way how I can pay for the products. But if I go to the supermarket without cash, but I have mobile money, then I can use mobile money to pay for the products. If I go to the supermarket with the cash, but without mobile money, I can use cash to pay the product. If I go to the supermarket with the cash and mobile money, yes, I can also move out with the product. That is the all what? The all get. And the condition on all get is it can only return the true if one or both inputs are what? Are true. The way you have seen us trying to deal with the supermarket purchase here. Allow me to read people's comments here. Okay, Brian says, so what about the multiple gate that you were showing that? First, okay, we are going to look at that also. Then, okay, so why logic gets important in the modern day electronic computers? It is because these electronic or logic gates or a combination of them, it is what helps the computers to perform complex operations and the tasks at a very high speed that you may not even realize. So basically, like whatever complex task you may assign to a computer, then it is because that a computer has these logic gates which are in millions that makes it very, very possible and easy for it to do what? To execute your what? Your particular task that you have assigned it. Yeah. Okay. Mogisho says my voice is low. Kindly confirm if it has improved a bit. Just to confirm, then we can see what to do. Okay, thank you for the feedback. Mogisho. Okay. Another gate I want us to talk about is the NOT gate. Let me see. Let us first go back here and confirm. Okay. Let us look at the NOT gate. I didn't arrange them properly according to what I want to showcase to you. But let us first look at the NOT gate. Now, the NOT gate is represented by, let me see if I included the symbol here for the NOT gate. Okay, okay, very good. You will have okay. Yeah, I just wanted to first to show you the symbol for the NOT gate. This is what I was looking at. Yeah, and the NOT gate, some researchers and the books call it, they also call it a logical inverter. because for it has only one what? One input, not multiple inputs, the way we have been dealing with A, input A, then input what? Input B for us to get the output. In this case, we only have one input and the what? The output. So whereby if the input is true or one, then the output is zero and vice versa. The way how you see here. If the input is false or zero, then the output is the opposite. If the input is true or one, then the output is what? Is the opposite. I don't know if you're getting, these are the ones that we have been dealing with in what? In
The full time fit my pinky.
they all
That's still something I'm going.
Excuse me, sir.
yes, Matthias.
You know what's going through my head?
Malinga first mute so that Matthias can speak. Matthias, go on.
So on the truth table there, I'm saying we have graphical, algebraic, and free table, truth table. I thought that F is an output of A and B. Also, F is concluded in the table. Is included in the table.
Hello? Matthias.
I'm asking on the AND gate, the first one, F and O gate. I'm not on the NOT gate.
Okay.
I'm seeing there F. You also included it on the truth table. Isn't it the final answer?
Yes. Now, here, the AND and the OR gates have multiple inputs. That is why you have input A and input B for us to get the output. The same appeals to OR gate, where we have the first input or input A and second input, which is input B, for us to get the output. And here we just have only one input, then that determines the output. Okay. Okay, now Maggie is asking, once you are asked to explain the logic of the different gates, what's the response? Now, the response should be in line with, the response should be that each gate has its own what? Logic or set of rules. So your response should be based on the rule that particular gate performs or determine, because it is the one that determines how it acts based on multiple what? Inputs. You get. For example, you remember we said for the issue of the AND gate, the output can only be true or one when both the inputs are what? Are also true. Then when we went to the OR, it says, or the condition is, it is true if one or both inputs are also true. You get. And when we came to the NOT, you realize that for it, if the input is one or true, then the output must be zero or false, and vice versa. You get. So your answer in terms of finding the difference should be based on the what? Should be based on the condition that particular or set of rules that determines how it acts based on multiple what? Multiple inputs in that sense. I don't know, and I'm not so sure if, yes, everyone is getting it the way how I intend to, I intend these things to sync. Mugisho says, let's assume we are referring her question to the OR gate. How can you comment on the output B? Her question was, explain the logic of the different gates. What is the rest? Explain the logic of the different gates. What is the response? Actually, I thought her question she was interested in knowing, but she can clarify since she's here. She can clarify. I thought she wanted to know the difference between the different the different gates. Yeah, whereby but when now I read it, it is like once you are asked to explain okay. Hey, we have Brian. We have Brian. Brian says he gets it well. Yeah. And I think where possible, always feel free to come in. I mean, anyone can also add a submission. Yeah, because I want it to get into each and everyone's, memory in a proper way. So if we have a different version, it can also be welcomed. Yeah. Before Brian answers Mogisho's question, let Maggie first unmute and ask her question properly. Maggie, unmute and talk to us.
Good evening.
Yes, good evening.
My question is, in case they ask you the logic, for example, they may ask, what's the logic behind this gate? They give you the AND gate alone, the OR gate alone, and the NOT gate alone. So what's the response for each gate?
And I told you that your response should rely on the condition that particular gate must follow fail. For example, the AND gate that both inputs must be what? True. For the output to be what? True. And when one of them is not, then obviously the output is also what? A false or a zero. So let Brian also, Brian, if you are there, can you unmute and try to also add a voice on this? Then we can see.
Okay, thank you, sir. So I remember for those of us who are doing that course unit of computational math with Mr. Lokolimo. So we passed upon this that was in Boolean algebra. So for the AND gate, that one, we say that it is an arrangement in a series. So he even gave us an expression like if you use taps, if two taps are in a series, water can only come out of the other flow when all of them are open. If one is blocked, then water will not come. So meaning that the result is always true when both are on, when it is 1 and 1, all the taps are open. Then for the OR gate, he explained to us that is an arrangement in parallel. So in parallel, it means that if one tap up is open and one is closed, it means water can pass up until it reaches the final destination. So that means if one is open, then the output is a true, it's 1, because at least can pass there. So the rule stood there that it is always false when all of them are false, when all the logic units are false. Then of course the NOT gate, that one, the inverter, it's always the opposite. If it is on, then the result is not on. If it is not on, then the result is on. With even the diagram, looked at them. So I think, personally, as we looked at it, I think it would not be so new. That's simply what I can simply talk about it, sir. Thank you, sir.
Okay, thank you so much. Thank you so much, Brian, for the supplement on this, as well as the amendment, and in programming we call it refactoring. So then we have Eugene. Eugene says, so to all gets, is it applied that all inputs should be true for the result as output? For the result as output to be true? So sir, to all gets, is it applied that all inputs should be true for the result as output to be true? Have I gotten the reason? I mean the question properly? Is there anyone who can help us on this? Depending on how you have understood is a question. Anyone with a response on Eugene's
Sir,
Okay,
sir,
okay.
but the AND gates.
Okay.
So
Robert.
the AND gates, we have an example
Robert.
of electricity. Like the moment you're having a
Robert, continue.
So when we are having a switch, we find that in our switch we want to have a truth value in the AND gate. So the moment you have one output which is false and the other output is true, that one becomes also false. Like the output that you're going to get becomes false. But the moment you have both truth values in one output, you have A is true, then it's also true. The other side, the output is going to for that AND gate. But you have a false value, like you have in A, and then in B you have 1. So the other output, the other side, is going to be 0, because in AND we want all values to be true, which is 1.
True.
So that's how I've understood the AND gates.
Is there any other person to respond? Okay, Maggie wanted also to say something on Eugene's question. Maggie, if you're still there, please unmute and add the voice.
Okay. Let me add on this. It is now like the simplest example is like if you're adding a number, like, I mean, you're multiplying a number, you multiply 1 times 0, it is 0. Then if you multiply 1 times 1, you get 1. So that is for AND gates. So the moment you're having a place, or you're having an output which has 0, and then the other output has 1. So if you multiply 1 times 0, you get 0. But if you have output which has 1 on A and an output which has 1 in B, then you multiply them all together, you get 1, which is a true value.
All your responses really, makes it very, very simplified and clear, unless maybe someone has just a different view. Maggie, I don't know if your submission was also on the same, but please unmute and have something to say. Otherwise, Robert, thanks a lot for clarifying on the above. Maggie, are you still interested in coming on board? Oh, yeah, Maggie has confirmed that it is the same. That is what she wanted to do to also give clarity on. Where's Helga? Helga, are you there?
Yes, I'm there.
Okay. Any other question before we can move on to the next part? Any other question regarding at least those three logic gates?
Yes, we are fine so far.
I have a challenge that we have some individuals who did not, or who have not been doing what? Who have not been doing courseworks. Yet we are almost concluding each and everything. And now it becomes hard, if not impossible, for such an individual to do what? An exam, because you know our rules. For someone to do an exam, you must have passed the what? The coursework with at least 50%, which is 25 out of 50. So, but there are some members without what? This. And I have already arranged a small other task that I want you to do to confirm if what we have discussed has also is sinking into your memory before we can prolong this to further discussions. Otherwise, anytime I will be updating your class reps in case we have any new arrangement regarding, because I want us to add something here. But I have already shared the material on what? On Moodle. Feel free to go and access. But also the assignment link is also gonna be activated, where you will be required to submit your assignment regarding the today's session, as well as the material that I have attached on Moodle. And then probably, God willing, next week the results can be out from all the what? The assignments. But also in case of any new arrangement for our meeting, if we are to have other meetings, I will be communicating to your class reps, and then we can see what to do. But if for the case of this assignment I'm putting right now, everyone must do. Yeah, make sure that you comply and do for your own good. Yeah, so I wanted us to use this hour, and I am requesting to terminate, but before I terminate, I can see Jemba's hand is up. Jemba, unmute and speak to us.
Good afternoon, everyone.
Good afternoon.
Yeah, afternoon. We are starting, like, is it right now?
I didn't hear you.
Like, what's the period? Because you've talked about the assignment. Is it right now, or it is like some other day?
It is right now. I'm just going to activate it. It is already there, but I'm just going to activate it. So maybe,
Okay.
yeah, you can check any time, but today it is there.
Right.
So members, allow
Excuse
me. Yes.
Excuse me.
Matthias, go on.
The deadline. When is the deadline, sir?
Deadline can be tomorrow. How do you see? It is a simple task. It is a simple task. I don't want to give something hard at the same time. I understand you have even other assignments from other courses. So the more it takes so many days, the more it occupies you. And so Emma, what is your view?
I know. I was asking almost the same question, but it's
Okay.
okay, so we shall do it.
Okay, okay. Yeah, it is not complicated at all, please. Otherwise, have a nice evening. Bye for now.
Okay, thank you, sir.